All right, so in our previous lesson, we talked about the two different rates of change, and then we discussed average rate of change. Now we're going to discuss instantaneous rate of change. So think about the hot dog question. We said average is over the whole time. If we narrow in on a specific moment in time, how quickly are hot dogs being eaten at this exact minute? That's what we want to think about when we think of instantaneous rate of change. Instantaneous rate of change, we said, is more of like an estimated value because we don't have the calculus methods that we would use to calculate exactly what instantaneous rate of change is yet. So what we'll do is we'll estimate instantaneous rate of change by using some average rates of change, and we'll try to make that interval for the secant line as small as possible to calculate. The best estimate that we can get is when we make that secant interval as small as we possibly can, and the smaller we make it, the more accurate our estimate will be. So I'm going to show you a couple ways that we can estimate instantaneous rate of change. So this is actually the graph that we were looking at the end of our last lesson. This is the same quadratic. And I'm going to show you two methods that we can use to estimate instantaneous rate of change at 2 seconds. So at this specific point, we want to know how fast is height changing with respect to time. So remember, this represented height, and this represented time in seconds. And this is height in meters. So let's suppose that we didn't have an equation to help us with this. If we just had the graph, method one would be a good method if you just have a graph. And what we'll do is we will draw a tangent line. So for this unit, it would be helpful if you have like a little ruler that you can bring with you. If you don't have a ruler, just use some kind of straight edge for now, but bring a ruler next week. And method one is really just, we want to try to draw the best tangent line we possibly can that just skims the function at this exact point right here. And we want to try to balance it along the function so that it feels equally distributed on either side. So it is helpful too if you have like a clear ruler. That's even better because then you can kind of see the function from both sides. I just want this to be 1 point. Okay, so when I create my line here, I want to create it so that it's just skimming that point exactly. And then you can kind of decide with your ruler how exactly you want to place that so that this looks like it's kind of equal on both sides. So I might adjust this a little bit just so that it's, and then I would just extend it across like your whole graph as well because we want to see if it happens to hit through like some specific points that we can use. Okay, so again, my tangent line might be slightly different than your tangent line because it depends exactly how you balance that. That's why this is an estimated value. So in method one, we'll just try to find the slope of the tangent. And I'm going to do that by just choosing some points on this tangent line. So actually, my line happens to go right through this point right here, which is the point 3, 4. So I can use that as one of my points. And then the other point I might use is at 2. So I'm going to just, again, we're pretending we don't have an equation here for this method. So I'm just going to estimate this. I think this is approximately 9.5. I don't know exactly what that is, but it looks like 9.5 to me. Again, that's another reason why this is an estimated value, because if we didn't have an equation, we would have to estimate where these points are. Okay, so I'm going to use this as my x1, y1, and I'll use this as my x2, y2. Yours might be slightly different depending on how you drew your tangent line. So basically just choose 2 points that are on your tangent line, and you'll find the slope of your approximation of that tangent line, okay? So I'm going to say that slope equals, and because this is instantaneous rate of change, I'm going to use dy over dx. So it still means the change in y over the change in x, but We're just indicating that we're finding an instantaneous rate rather than an average rate. Okay, so I'm going to do y2 minus y1 over x2 minus x1. So I'm getting negative 5.5 meters per second. Yours might be different if you chose 2 different points on your tangent line, or if your tangent line was drawn slightly different than what mine was drawn as. And that's okay, but we should all get something kind of similar to this value. Might be like a couple decimals off either way, but it definitely should be negative. We know that for sure. We know that the tangent line has to go down toward the right in order to be a tangent line at this point. So we all should expect to get something negative. Decimals might be off. That's okay. It's an estimate. Okay, any questions on that method, Michael?
What's the difference between f equals dy over dx and f equals delta y over delta x?
Can anyone answer this question? What's the difference between dy over dx and delta y over delta x? Emma?
There is no difference. You're just waiting for the answer.
Yeah, so no difference. It's still y2 minus y1 over x2 minus x1. This just means we calculated an average, so a secant line slope over an interval. This is instantaneous. Okay, so it's just a notation to indicate what type of rate we're finding. Okay, perfect. Let's look at method 2. So method 2 is a good method if you have an equation. If you have a combination, like in this question, we actually have a combination of an equation and also a graph. You could try both methods and see what both methods give you, but the equation method is going to give you maybe a little bit more of an accurate answer. So I would go the equation route if you can, rather than drawing a tangent line, because that's like highly, it might be different for all of us, right? Whereas the equation would be a little bit more similar. So method 2, we're going to use some intervals to see if we can use average rates of change to estimate instantaneous rates of change. So we're going to create an interval surrounding 2. And the idea behind this is like if I were to choose, let's say, 1 to 3, and then if I narrow this interval even more, let's say I choose the interval from 1.5 to 2.5. Here's a secant line for that. See how these slopes are kind of similar to the slope of this tangent? So the closer I make this interval around 2, so if I moved this right on the opposite sides of 2 here, and I created a secant line there, that's going to be even more similar to the slope of what my tangent line should be. So the smaller I make the interval around there, the smaller, the closer my estimate will be to what the actual tangent line is. So that's the thought behind this method. So let's say we were to go from, sometimes we'll also just go from the number to like another number and then move this point in closer so that our secants will sort of approach the tangent from either side. So you might see that in some of your homework as well. Okay, so let's say we chose, for instance, the interval from 1.5 to 2.5. That's the interval that surrounds 2, right? I'm going to use the equation. This is going to be time 1 and time 2. I'm going to use the equation to calculate the heights at these times because I think they're not quite on exact cross sections. This one actually looks like it is, but we're going to pretend we don't have a graph, right, to do this if we just had an equation. So let's calculate h at 1.5 and h at 2.5. Okay, so just subbing it in to this equation here. So I want everybody out there calculating so we can get some answers pretty quickly here so we don't have to spend lots of time calculating these. Jake, what'd you get?
Well, I don't have an answer, but
okay.
would it be even more accurate if you did like 1.9, 2.1 or something?
Yeah, so we're gonna get to that actually. Did you get an answer?
No, I just had a question.
Sure.
How did you pick those 2 points? Like just based on the equation?
So I chose it because we want the exact instantaneous rate of change at 2 seconds. So I chose two surrounding values for 2 seconds, which is 1.5 to 2.5. And then in this process, we're going to narrow the interval down as Jake suggested. So just check what you have that you're trying to figure out the instantaneous rate of change for. Sarwa? So should I round this to 6? Is that what you're saying?
Like it's 5 to the last 6.
Oh, okay. So that's right?
Yeah.
Okay. Okay, and 2.5, anyone have this one for us? Pero? Okay. I think we calculated that one last time too, so that's good. Okay, so if we were to find the instantaneous rate of change, we would do delta y over delta x, or I guess I should have been using delta h over delta t. So dh over dt, I might actually just change this one as well to align with our variables, dh over dt. And that will be equal to h2 minus h1. So let's call this h2, h1. This will be x2, x1. 5.357 minus 10.975 over 2.5 minus 1.5, which is really just 1. Let me know what you guys get. Ian, what'd you get?
I think it's 5.6.
And that would be meters per second. So very close actually to our estimate of our tangent line from above. That's good. So Jake rightly suggested, wouldn't my estimate be even better if I shrunk that interval even more? Suppose I chose like 1.9 and 2.1. Or could I even choose 1.99 and 2.001 or something like that? I probably could, right? So suppose we made this interval even smaller. Let's make this 1.99 and 2.01. That's super close to right around 2. Like we're basically kind of like choosing 2 points that are so close so that we can find the secant line and hoping that that will be just about equal or a very good estimate for our tangent line. So let's see how much closer we can get with like an interval like this. So firstly, I want to calculate h at 1.99 and h at 2.01. Okay, so I'll let you guys calculate each of those. Any answers for either of these yet? Keaton?
H at 1.99 is 9.456.
Okay. And 2.01. Ian?
At 9.344.
344? Okay. Perfect. So this will be time 1 and height 1. This will be time 2 and height 2. And let's find the change in height over the change in time. We'll do 9.344 minus 9.456 over 2.01 minus 1.99. And this should be an even better estimate than this one is. So this will be really, really close to the actual tangent value or tangent slope. Okay, let me know once you've got an answer out there. Clayton, what'd you get?
Negative 5.6.
You got exactly 6 again?
Yeah.
Did this one have decimals on it? Or was it exactly 5.6? Oh, so it did have a couple decimals then. Does this one have decimals?
No.
Okay. Okay, so this one's probably the more accurate one. This one had a couple decimals on it. Yep,
So when I did like method 1, I used the point that was on my transit line,
yeah,
and I got -5. Just like -5
Yeah.
seconds.
yep,
Is that like an okay range to that?
that would be okay. Yep. Okay, so we were super close, which is good. Or I was. Keaton, not as close, but that's okay. But yeah, so as we make the interval smaller when we do actual calculations, the closer our estimate will be to the actual slope of the real tangent line. Of course, our tangent line that we drew might not be the actual, real, perfect tangent line because we're estimating approximately where to put that, right? So this method is always better than this method, but sometimes we don't have an equation. So if we only have a graph, we can estimate with the graph. If we only have an equation, we can do this method. Or if we have both, we could estimate both ways. Okay, let's look at a table example. So that was graph and equation. If we have a table, it's a little bit different because we just have like a finite set of data here. We just have like specific times, specific days, and specific temperatures on specific days. So over a 2-week window in July, the temperature is measured at 1 p.m. on random days. Find the instantaneous rate of change in temperature with respect to time on day 7. Okay, so how is the temperature changing with respect to the day? So method 1 would be we choose a surrounding interval. So this is the interval that, of course, surrounds 7. It would be the interval from 5 to 8. And we already have our values for this. It's 35.5 and 31.2. So if I'm finding, I'll do delta t over delta, I guess it's also time. So we can say, I'll say delta day. Change in temperature with respect to the day. And then I'm going to, oh, sorry, it would be the day with respect to temperature. Switch those. Time is the independent variable. So, no, sorry, I was right the first time. Never mind. Keep it the same. I'm thinking time is t. I'm getting confused. Okay, so change in temperature over the change in the days. So 31.2 is day 8, and then I'm going to subtract day 5, 35.5. And then I have to do it in the same order for this bottom calculation, 8 minus 5. And we'll get our approximate change in temperature with respect to the change in days. Okay, just make sure you're consistent with which one's your 0.1 and which one's your 0.2. These should happen at the same locations here and here. Okay, what do we get? Clayton, what'd you get?
-1.43.
And this is degrees Celsius per day. Okay, so over that span, we are losing approximately, or we're going down by 1.3 degrees per day and measured in Celsius. Okay, so that is a method that we can use. We can choose the surrounding interval if we have a table. Yeah, Keaton?
If it's going down on the 5th day, it's lower than on the 7th day. So it's going up.
So because we chose a surrounding interval, we're only taking into consideration this piece of data and this piece. We're not taking into consideration that middle piece, which actually brings us to our next part of the question, which is maybe a more accurate way is to average the two intervals over from 5 to 7 and 7 to 8. This would be only a method that we would use if the independent variable, so for instance the days, is not changing by a constant rate. If this was going up 1, 2, 3, 4, 5, 6, you'll get the same answer if you do the surrounding interval as if you were to do the two intervals on either side. But this one is just random days, right? It's 1 to 2, and then it's 2 to 5, and then it's 5 to 7, 7 to 8. So In this case, if I do the two intervals on either side of 7, including 7 in that data point, as Keaton said, it might give us a more accurate reading because it actually does go up from day 5 to day 7, and then it goes down after that. So I only do this when this is not changing by a constant. So 1, 2, 3, 4, 5, 6, or 2, 4, 6, 8, 10, and so on. This one's a bunch of different random days. So we're going to do 5 to 7, and then we'll also do 7 to 8, and then we're going to take the average of our two answers. So the change in temperature over the change in the day from 5 to 7. So 7, 36.1 degrees minus 35.5 degrees over 7 minus 5 for the first one. Okay, and what do we get? Okay, everyone needs to be calculating so that we can get answers here. Michael, what'd you get?
0.3.
0.3. Anyone else? That's all the decimals? Okay. So 0.3 degrees Celsius per day. Okay, then we're going to do 7 to 8. So the change in temperature over the change in time. So this will now be my temperature 2 and my temperature 1. So I'll do day 8's temperature minus day 7's temperature. And then I'll do over day 8 minus day 7. Rebecca? Negative 4.9. Everyone else? Yeah? Is that all the decimals? Okay.
For this unit, does it matter if
No. That only matters if you're pressing sine, cosine, tan on your calculator. Okay, and then we do the average. So we want to average both. How do I take an average of two values? Add them and divide by 2. So 0.3 plus negative 4.9 divided by 2. Degrees Celsius per day. So this is actually a more accurate estimate for exactly how the temperature is changing at day 7 than this one was. Again, I only need to do this if my independent thing, so time or the date or whatever the independent variable is changing by random amounts rather than constant amounts. Because this answer and this answer will be the same if it's changing by a constant amount. So only needed if independent variable changes by different values. Okay? So this will be the better answer in this scenario. But this is useful if your independent variable is changing by a constant rate. You can just do this. Okay, last part for instantaneous rate of change. This is an instantaneous rate of change table that we can use to observe what is happening with the slopes of the secants as we narrow in on an interval, so similar to method 2 from our first example above. These charts really help us kind of ground ourselves in like what calculus is doing. So these charts are important. I know we want to maybe flip, maybe we want to go to the interval that's like the closest interval already, but it's good to be able to observe what the slopes of the secants are approaching. So I've filled in one for us here. We calculate delta y, we calculate delta x, and then we just calculate delta y over delta x. So it's just a more formal table for what we did above in example 1. So we already know, actually we didn't really calculate it here, but when I sub in 2 into this function, y will be equal to, I'm going to do a couple of calculations down here. When I sub in 2, it's 3x squared minus 1. So I'll get 4 times 3 minus 1, which will give me 11. So this is when x equals 2. So I have all the y's for when x equals 2 for all of these parts right here, right? What we need to calculate is all the y's for these, each of these values. So before I do the table, I'm just going to take a moment with your help in calculating some of these. We're going to take a moment and we're going to plug each of these x values into our function. So I want to know what is y when x is 2.5, so sub that in. Then I want to know what is y when x is 2.1. And I want to know when x is 2.01, what is y? Okay, and I also want to know 2.001 as well. So I'm going to add that at the end. Okay, so let's calculate for each of these here what the y's are quickly. I need everybody to be calculating. Maybe a couple people can take different ones rather than starting right at the beginning here. And then we can get them really quickly. Pause the video while we... All right, so here's the calculation for all of our y coordinates. Each time you do a calculation here, we're going to use this one because this is in every single interval, and then we'll change all the other ones as we go along to each interval. So when I want to calculate this, think of this as like your x1 and your x2. When I calculate delta y, I want to do the difference between f at 2.5 and f at 2. So we found f at 2.5, or y at 2.5, to be 17.75. And we know our value when x is 2, our y value is 11. Sorry. Okay, so we'll get 6.5. Delta x will be x2 minus x1. Will be 0.5. And then when we do delta y over delta x, we'll do this over this. So I believe we'll get 13 for that. Okay, then we're going to think of this as our x1, x2 for the next calculation. So when we do delta y, I'll take the y of 2.1, which is, yep, Sarah, did I do something wrong?
For delta y, what is this? 6.75? This 17.75?
I got 17 point, oh, sorry. I thought it was 17.5, yes. So let's fix that. Sorry, that was right. Sorry, I read 17.5, so yes, 6.75. And then 6.75 over 0.5. Sorry, thank you, Sarwa. So 13.5 then. Okay, y2 minus y1 for the next one. So 12.23 minus 11 gives us 1.23. And then delta x, 2.1 minus 2 gives us 0.1. And then just take each of your answers from your columns and divide. So 1.23 divided by 0.1. So lots of just adding and subtracting and dividing calculations here, which we all can do. So 12.3. Okay, last ones, delta y. So now I'm going to call this my x1, x2. So I'll take my y2, which will be this one, 11.1203, minus my y1, which will be 11. And we're going to get 0.1203. And delta x, 2.01 minus 2, 0.01. Okay, keep all your decimals until you make a final decision here on your column trend. Okay, last one. So let's call this x1, x2. I'm going to do y2, which is 11.012003 minus 11. We'll get 0.01003. And then 2.001 minus 2. And then we're going to calculate delta y over delta x. Okay, so really what we're interested here is the trend as we move lower in this column. And we will call this is going to be our first introduction to the concept of what we call a limit. So limit is essentially just something that is being approached. So as we go down in this column, what are the slopes of the secants slowly approaching here? What value could we maybe guess? What was that? 12. Okay, so these are getting closer and closer and closer to 12. If we were to make an interval that's even smaller than this one, we would assume that we'll get 12.0003 or 12.000003, depending on how close we make it. So we would say that our approximate instantaneous rate of change, we'll use this little subscript of x equals 2 to say instantaneous rate of change when x equals 2 is equal to 12, because that's the trend that we can see in the slope of the secant column. And we would call this the limit of secant slopes. It's the value that's being approached. Yes, it's very important that it's all caps. No, I'm just kidding. It doesn't. Okay, so has anyone seen the movie Mean Girls before? And she answers the question, the limit does not exist. This is your first step to understanding that part of Mean Girls. Okay, so this is a big moment. All right, so this is just our first intro to limits, but we'll talk more about limits later. So we've got a half an hour today. Let me see what we'll do. I'm going to pause this first.